In episode 31, titled Matrix Operations You Must Understand, Multiply, Transpose, Invert, Decompose, the goal is to master the core matrix actions that power many methods, because DataX questions often assume you recognize what these operations accomplish even when they are described indirectly. You are not being tested on being a symbolic manipulator. You are being tested on understanding what the operations do to data, why they appear in modeling workflows, and what can go wrong when their conditions are not met. Matrix multiplication, transposition, inversion, and decomposition are the backbone moves behind regression, covariance reasoning, dimensionality reduction, and many optimization routines. When you know their meaning, you can interpret method descriptions quickly and avoid common traps about shapes, invertibility, and numerical stability. This episode will keep the focus on purpose, alignment, and practical consequences, because that is what the exam rewards. You will also practice dimension checking, which is the simplest way to prevent nonsense operations and to detect distractors that rely on shape confusion. By the end, you should be able to say what each operation is doing in a modeling context and verify that it is valid. Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Matrix multiplication is the operation that combines transformations and feature weights, and it is best understood as applying a linear rule consistently across many vectors. When you multiply a data matrix by a weight vector, you are performing a dot product for every row, producing a score or prediction for each record. When you multiply two matrices, you are composing transformations, meaning the output is equivalent to applying one transformation and then another in sequence. This is why multiplication is everywhere in modeling, from linear regression to neural network layers, because it is the efficient way to map inputs into outputs at scale. The exam may describe applying weights to features or transforming the feature space, and matrix multiplication is the underlying action. The key practical point is that multiplication requires alignment of dimensions, meaning the inner dimensions must match, which reflects that the transformation must be defined on the vector space you are feeding it. DataX rewards multiplication intuition because it helps you see that models are often repeated applications of linear transformations, not mysterious black boxes.
Transposition swaps rows and columns, and it is primarily useful for alignment and for expressing certain calculations in compact, consistent forms.
If you view the dataset as a matrix with rows as records and columns as features, the transpose flips that view, turning rows into columns and columns into rows.
This matters because many formulas and computational routines require a particular orientation, such as treating feature vectors as columns or treating observations as columns, depending on the convention.
Transposition is also central for creating products like a matrix multiplied by its transpose, which can produce covariance-like structures or gram matrices that summarize relationships. The exam often expects you to recognize that transposition is not changing the data values, but changing the orientation, so operations can align and produce the intended results.
This is why transpose appears in least squares expressions and in covariance calculations, because those computations involve combining information across observations and across features in a structured way.
When you treat transpose as reorient for alignment, you will not overcomplicate it, and you will recognize why it appears so often.
Matrix inversion represents undoing a transformation, but only when invertible conditions hold, which is a crucial exam nuance because inversion is frequently misunderstood as a universal operation. If a matrix represents a linear transform that is one-to-one and covers the space fully, then an inverse matrix exists that maps outputs back to inputs, effectively undoing the transform. In many modeling contexts, inversion appears conceptually when solving a linear system, such as finding coefficients that satisfy a set of equations under certain conditions. However, not every matrix can be inverted, and the existence of an inverse is tightly linked to properties like having full rank and being square in the conventional sense. The exam may mention solving for coefficients or undoing a transform, and inversion might appear in the background, but you should also be ready to recognize when inversion is not appropriate or not stable. In practice, many algorithms avoid explicit inversion because it can be numerically unstable, even when an inverse exists in theory. DataX rewards learners who understand inversion as conditional, not automatic, because that understanding prevents wrong conclusions about solvability and stability.
Singular matrices are non-invertible due to redundancy, meaning they do not contain enough independent information to define a one-to-one mapping.
Singularity often arises when columns are linearly dependent, such as when one feature is a combination of others, or when there are duplicate or perfectly correlated features.
In those cases, the transformation collapses dimensions, mapping different inputs to the same output, so there is no unique way to reverse it.
The exam may describe multicollinearity, redundant features, or a system where there are more parameters than independent data supports, and those are singularity cues.
A singular matrix can also appear when there is insufficient variation in the data, such as a feature that is constant or nearly constant across all records.
Recognizing singularity is important because it explains why some regression problems do not have unique solutions and why naive inversion-based formulas can fail. DataX rewards this recognition because it connects linear algebra properties to practical modeling issues like unstable coefficients and unreliable inference. Decompositions are used to simplify problems into stable components, and they are often the most practical way to understand and solve matrix-based tasks without relying on fragile inversion. A decomposition expresses a matrix as a product of simpler matrices that capture structure, such as directions of variation, scaling factors, and orthogonal components. The point is not to memorize every decomposition formula, but to understand that decompositions reveal hidden structure and can make computations more stable. In modeling, decompositions help you reduce dimensionality, identify latent factors, and solve least squares problems in ways that are less sensitive to noise and redundancy. The exam may describe breaking a matrix into components, finding principal directions, or discovering latent structure, which are all decomposition cues. Decomposition also supports diagnosing rank and redundancy because the decomposition often reveals how many meaningful components exist. DataX rewards decomposition intuition because it underlies methods like principal component analysis and supports stable numerical computation in real pipelines. Common decompositions you should recognize by name and purpose include eigendecompositions, singular value decomposition, and factorization ideas, even if you are not asked to compute them. Eigendecomposition is associated with square matrices and can reveal eigenvalues and eigenvectors that describe how the matrix stretches or rotates space along certain directions. Singular value decomposition, often shortened as SVD after you have said singular value decomposition, generalizes the idea and works for many rectangular matrices, revealing singular values and orthogonal directions that capture the most structure.
Factorization concepts include breaking a matrix into parts that reflect latent factors, such as low-rank approximations used in recommendation systems or dimensionality reduction. The exam tends to test these at the level of what does this enable, such as finding principal components, compressing information, or solving least squares robustly. You do not need to reproduce the decomposition steps, but you should recognize that these methods expose structure that makes learning and computation more reliable. DataX rewards this recognition because it shows you understand why decompositions are used in the first place. Transposition connects directly to covariance calculations and least squares formulas, which is why it appears frequently in linear regression contexts. Covariance-like computations often involve multiplying a centered data matrix by its transpose in a particular orientation to summarize how features vary together. Least square solutions often involve transposed matrices because the algebraic forms require combining information across all observations to compute coefficient estimates. The exam may not present the exact formulas, but it can describe operations like compute relationships among features, or solve for coefficients using matrix operations, and transposition is a key part of that structure. Transposition is also what lets you align vectors and matrices for multiplication when one object needs to be a row vector versus a column vector under a chosen convention. This is one reason the exam emphasizes understanding, not memorization, because conventions differ, but the purpose of transposition remains the same. DataX rewards learners who understand that transposition is often about making the shapes match so that cross-record and cross-feature information can be combined correctly. Inversion is connected to solving linear systems in regression contexts, but the exam expects you to understand it as part of a solution idea rather than as a recommended computational step. In regression, one way to express a coefficient solution involves a matrix inverse under ideal conditions, which captures the idea of solving the normal equations. However, practical computation often uses more stable approaches, such as decompositions, because explicit inversion can amplify numerical noise. The exam may test whether you understand that inversion requires non-singularity and good conditioning, and that redundancy makes inversion impossible. It may also test whether you know that solve a linear system is the goal, and inversion is one conceptual route, but not necessarily the safest computational route. This is why numerical stability matters. In real systems, stable computation can matter more than a neat formula. DataX rewards this because it reflects applied expertise, where you know both what the math says and how it behaves in practice. Numerical stability concerns show up when naive inversion approaches are used, because even invertible matrices can be ill-conditioned, meaning small errors in data lead to large errors in computed results. Ill-conditioning often occurs when features are nearly collinear, when scales differ dramatically, or when the matrix has a wide range of singular values, all of which can amplify rounding and measurement noise. The exam may describe unstable coefficients, wildly varying solutions across runs, or sensitivity to small changes, and those are stability cues. In such cases, decomposition-based solutions and regularization ideas can provide more stable behavior than direct inversion. The key is to understand that invertible, in theory, does not guarantee safe to invert in practice, which is exactly the kind of practical nuance DataX likes to test. Stability also connects to pre-processing because scaling and normalization can improve conditioning and reduce numerical issues. DataX rewards this awareness because it shows you can reason about reliability, not just about symbolic correctness. Dimension checking is the simplest and most reliable way to validate whether an operation is meaningful, and it is a common exam skill because many distractors rely on shape confusion. For matrix multiplication to be valid, the number of columns in the left matrix must equal the number of rows in the right matrix, which is the alignment rule that reflects compatible transformations. Transposition changes a matrix's shape by swapping rows and columns, which can make multiplication possible when it was previously misaligned. Inversion, when it exists in the standard sense, applies to square matrices, and a practical way to think about it is that you can only undo a transform that maps a space to itself without collapsing dimensions. Decompositions produce multiple matrices whose shapes multiply back to the original, and their shapes reflect how many independent directions are present. The exam may present a scenario about data shape, features, and observations, and the correct answer may require recognizing whether an operation can even be performed. When you practice dimension checking, you prevent basic errors, and you can quickly eliminate answer options that are mathematically inconsistent. Decomposition intuition also sets you up for principal component analysis and latent structure discovery because those methods rely on breaking data into directions that capture meaningful variance. Principal component analysis uses decomposition ideas to find orthogonal directions that represent the major patterns in the data, allowing you to compress information while preserving structure. Latent structure discovery extends this idea to finding hidden factors that explain observed behavior, which can be useful in recommendation, topic modeling, and other contexts where observed variables reflect underlying drivers. The exam often frames this as reduce dimensionality or find underlying factors, and decomposition thinking is the bridge that makes those phrases concrete. When you understand that decompositions reveal stable components, you can choose methods that are appropriate for noise reduction and redundancy management. This also ties back to rank because the number of meaningful components is linked to how much independent information exists in the data. DataX rewards this because it reflects integrated understanding of why matrix operations matter in real modeling workflows. A useful anchor for this episode is that multiply combines, transpose reorients, and decompose reveals structure, because it captures the practical role of each action. Multiplication is how you apply weights, combine transformations, and produce predictions at scale. Transposition is how you flip orientation so that calculations align correctly and so that covariance and least square structures can be expressed and computed. Decomposition is how you break a complex object into stable pieces that are easier to interpret, compute with, and use for dimensionality reduction. Inversion fits into this story as the conceptual undo when it exists, but the anchor helps you remember that decomposition is often the safer and more revealing route. Under exam pressure, this anchor lets you answer "what does this operation do?" questions without falling into symbol anxiety. DataX rewards this because it prioritizes functional understanding over rote recall of formulas. To conclude episode 31, do a dimension check aloud and then confirm operation validity, because this is the most reliable way to avoid mistakes and to defend your reasoning in exam-style prompts.
Start by naming the shape of the data matrix as records by features, then state the shape of a weight vector or transformation matrix you intend to multiply with it. Confirm that the inner dimensions align, meaning the feature count matches the length of the weight vector or the input dimension of the transformation. If the prompt involves a transpose, state that transposition swaps the shape and explain how that makes a multiplication or covariance calculation possible. If the prompt involves an inverse, state that an inverse requires a square, full-rank matrix, and that redundancy creates singularity, which blocks inversion and motivates decomposition-based approaches.
When you can narrate this check clearly, you will handle matrix operation questions with calm confidence and with the kind of practical mathematical judgment DataX is designed to reward.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit BareMetalCyber.com.